Good afternoon, and thank you for having me. It's a pleasure to be here, and I'm very happy to make a presentation to you today. First, I will begin with some background information about the company Nynas, and then some background information to the project work. This is mostly a very scientific presentation, and then it will go into the actual laboratory work, focusing on developing greases in low and high temperature applications, and then I'll have some conclusions. So Nynas is a very different kind of oil company. A traditional oil company will have a large sort of fuel yield, or the main focus will be on fuel production. The base oil production will be almost like a byproduct or a side train, and also a bitumen might be a small component of a typical base oil refinery production. But Nynas is a very different kind of company. We are smaller. We only have 900 employees, but we are operating in more than 30 countries with sales offices around the world. Our business is base oils, and we focus a lot on purchasing the right crude so we can get a very large base oil yield. We are also a naphthenics producing company, so we are only buying naphthenic crude oils. We also have a side bitumen business. Our business is very seasonal, as we are based in Scandinavia and Northern Europe, so we tend to produce heavy bitumen crudes only in the summer months when the bitumen production and sales takes place. A very small fuel component. We don't sell fuels, we just sell off the distillates to other companies. I am based at what we call our Nynas Technology Center, and this is just outside of Stockholm, south of Sweden, in a town called Nynäshamn. There we have our production facility, as well as approximately 40 people who are focused on research and product development. So there we have pilot plants, we have people who are focusing on developing a new process technology. We're always looking at new product developments, different application groups, etc. So just some background information into the work I'm going to present. This morning we heard how there's a lot of Group 1 closures happening in Europe. So the rationalization of Group 1, we think, will have a good opportunities for naphthenic oils. In the last 7 years, we've had several million tons of Group 1 oils disappearing from the market. And just in 2015 alone, we have seen announcements and notifications of 4 refineries that will actually stop their base train or the base oil production. In fact, a 5th refinery is already up for sale as well. So we think that 2015 is going to be quite a significant year in terms of the rationalization of Group 1 refineries in Europe. So we see that the shift in the paraffinic pool from Group 1 towards Group 2 and 3 will actually create technological challenges, specifically in industrial lubricants. And here we anticipate a gap in viscosity and solvency. And this is where we think that naphthenic oils can have a role to play. They can be used alone or in conjunction with Group 2 and Group 3 oils in applications where viscosity and solvency are challenges. So I see this as mostly in industrial applications, not engine oils or automotive applications. So when we talk about solvency gap, just to understand what that really means, in general, the base oil solvency affects the oil's capacity to dissolve large additive packages. It also keeps contaminants in solution, but it keeps deposits in solution. In greases, solvency is very important in the formulation. You have a better soap yield. You also have better interaction between the oil and the soap. In emulsions, because with naphthenic oils you have a a closer density to water. It's easier to formulate with surfactants. You have much more stable emulsions with naphthenic oils compared to paraffinic oils. So that is the solvency gap that we anticipate disappearing with the group 1 products. Viscosity, though, is another interesting dilemma. I have a table there with the different API groups, and you're familiar with the different light neutral, medium neutral, solvent neutral, and bright stocks. And those percentages of the yields that one typically gets out of those kind of productions. So if the group 1 yields have to completely disappear, here you will have absolutely no bright stock available. And likewise, no more heavy neutral and only a 20%. Group 2 and group 3 do not have the capacity to produce these products within these viscosity ranges. And again, this is where naphthenic oils can play an important role. So here I have plotted a slightly different graph, viscosity versus solvency. So group 3 having really quite a small viscosity range and also a lower solvency. Likewise with group 2, a slightly better viscosity range compared to group 3, but also limited solvency. Whereas with naphthenic oils, you can have quite a high solvency, and we have really high viscosities. We can have viscosities of 700 to 800 centistokes at 40 degrees C. So in the middle, we see a gap. And we like to think that we can look at blends of group 2 and group 3 with naphthenic oils in order to compensate for the lack of solvency and viscosity. So we like to think that we are providing a solution to the disappearance of group 1 from the market. Okay, so with this in mind, we decided to embark on a bit of grease work. So I took different type of base oils produced from different crudes, and they were also produced in different ways. So not only did I look at paraffinic oil versus naphthenic oil, but I also took different degrees of refining within the naphthenic oils to understand if a highly refined oil responds differently to a less refined oil. So once these oils were then taken and we made greases out of them, and I'll go into a bit more detail about that, we conducted flow pressure tests and rheological measurements in order to look at the low temperature properties, and then to investigate the high temperature behavior, we looked at rheological and tribology measurements as well. So the chemical and physical properties of the base oil are carried through into the greases. In the grease formulation, there is something like almost 90% the base oil. So therefore, it plays a very important part, and these characteristics are carried through. So typically, these are what you will find in base oils: paraffins, isoparaffins, naphthalene, aromatics, olefins. Of course, we have some sulfur, some nitrogen, some oxygen, but most of the refining processes are focused on removing these, what we call contaminants. I have there the chemical little diagrams there. I'm sure you're familiar with them. But typically, those chemical structures give rise to, in my comment section, those characteristics. So if you wanted certain characteristics in a base oil and you wanted those to carry through into a grease, you would perhaps make sure you had the right blend of those molecules. Sorry. So paraffins give rise to good VI, but of course, usually because they are normal alkanes, they are waxes and they tend to crystallize at low temperatures, so they give a very poor low temperature property. Also, poor solvency, they usually have a very high annealing point. Isoparaffins are much higher VIs. Naphthenics, which are ring-like structures, they are the low VI. They have very good sort of cooling properties, good low temperature properties, and good solvency. Aromatics, of course, has good solvency, but you don't want too much aromatics in the oils because they are, in some cases, hazardous and toxic. And a lot of the refining processes are focused around removing aromatics from the base oils. And then olefins as well, highly reactive. They tend to promote color degradation in the base oil and also sludge formation. So I just wanted to differentiate between how a group 2 oil is produced and an naphthenic oil, because later on I will specifically look at a blend of oils, group 2 and naphthenic. So group 2, of course, goes through a hydrocracking stage, and then either solvent, catalytic or isodewaxing, and then hydrofinishing. And each of these processes aims to achieve a certain thing. For example, hydrocracking, you are focused in on removing the aromatics, the sulfur and the nitrogen and any other impurities. And this is where you would control your viscosity index, your viscosity, and your color and your stability. And then for your solvent dewaxing, or your sort of removing of the waxing of the normal alkanes, this influences your pore point results, cloud point, your filterability characteristics. And then lastly, hydrotreatment, removing again the last bits of impurities and trying to make the oil even more refined. And here you get a better thermal stability and better oxidation stability. So with the group 2, it's a predominantly or exclusively conversion process. If we look at naphthenic oils at Nynas, we have 2 different ways of processing the crude. Firstly, we buy a wax-free crude, which means that we do not have any dewaxing processes in our facilities. Also, we tend to buy very heavy crude, so there is no atmospheric distillation unit, but we proceed directly into a vacuum distillation. When the crude is fractionated, and then you can have a solvent extraction by removing aromatics, and then a hydrofinishing to remove any sulfur, nitrogen, and other impurities. Or you could have a simple all-hydrogenation route, which is mostly what we have in Nynas and also in our Harburg facility. There again, we can fractionate the crude and then just go into quite a harsh hydrotreatment, removing aromatics, sulfur, nitrogen, and impurities. And again, sometimes we have a hydrofinishing stage as well. So here, it's no dewaxing at all. Okay, so these are the 5 different oils that I use to make the greases. So sample A, B, C, D. Sorry, A, B, and D are naphthenic, whereas sample C is a paraffinic. And I have in the next column the methods by which they were processed. And we can see that it influences the results quite a lot. Sample E is actually a blend of a group 2 and a naphthenic. And it's quite similar to sample A and C, but not 100% the same, but very similar. So here we can see the aromatic content varies quite a lot. So that means that you will have a different solvent power and you will see different yield results in the grease production. The annealing points, that's a typical high annealing point for a paraffinic type oil or a group 2 oil, whereas the naphthenic ones have a low, meaning they have a much higher solvent power. The sulfur contents are quite close, except for the solvent refined one. Not so much of the sulfur has been removed. The pore points are pretty similar, of course, except for the paraffinic oil, which has obviously more alkanes in them, normal alkanes, and therefore more waxes, and so they will crystallize out first. I try to keep the viscosities in a similar range, but I guess samples D and E are close. Okay, so at Nynas, at Nynas we have a small grease production pilot plant where we conduct research. So this is a small kettle, it's about a 10 to 12 kilogram capacity. And in this little pilot plant, we have made NLGI grade 2 greases based on lithium and 12-hydroxystearate acid. We used, if we were using any mixtures, those mixtures were used throughout the cooking and the cooling processes. There is a high-speed dissolving unit which we use as homogenization. It also has a pre-roll mold that we use to homogenize the sample afterwards as well. There are absolutely no additives in these greases, so these are just base greases, so perhaps easier to compare. So now we have the results of the greases produced. I tried to keep the penetration number within the same range so we could compare them. And immediately we can see that sample C, which was your paraffinic oil, requires a lot more soap in order to achieve the same NLGI grade. Sample A was the sort of less refined naphthenic oil, requiring less soap, whereas sample B, they're pretty much the same oils, but the one oil is more highly refined than the other, and we see that influencing there. Also, looking at the mechanical stability of the greases, we see that they are fairly comparable, even though sample A and even sample E has a much lower soap content. It still provides good mechanical stability. Sample E is now your blend of group 2 and naphthenic. So we see a good synergy, I think, between blending these two oils and producing a grease. So looking at the low temperature analysis, we decided to run some flow pressure analysis. So a flow pressure instrument is you have a very small nozzle that you pack with grease, and you put it in a small chamber, and you decrease the temperature to whatever you want, which is minus 35 and minus 20, and you apply a pressure, and you note the pressure at which the grease starts moving. That gives an indication of the pumpability of the grease at very low temperatures. So immediately we see, of course, that sample C, which has normal alkanes or paraffins in there, requires a lot more pressure to be able to move at these temperatures as compared to the others. Again, a very interesting result with sample E because it's a blend of sample A and sample C. So we see again very interesting synergies when you put together specifically a group 2 and a naphthenic oil. And these interesting synergies are carrying through into the greases as well. So in order to verify those flow pressure results, we decided to look at reológico measurements. So I'm sure you're familiar with the sort of Anton bar dynamic shear rheometer. For this particular experiment, we used a plate-on-plate geometry. We have the option of using cone on plate and several other geometries. The diameter, 3 millimeters, and then a force applied on top of 20 newtons, and then the sample is sheared, meaning that the top plate sort of starts spinning, and then you measure the response to the force applied. And then I ran a temperature sweep. So here we have a plot of running from 25 plus to minus 20, and this is the G prime or the storage modulus. So basically it's the amount of sort of the elastic part of the grease, or the pressure applied to get that kind of response. So the higher the number, the sort of thicker or harder the grease is. Now if you remember earlier on, I think the pour points were around minus 15 of the oil in sample C. But of interest here is we see that already at perhaps 0 or even minus 5, the graph sort of moves up almost exponentially. And so something happens quite, even though you might expect the pour point around here, we see that the grease or the molecules start crystallizing quite early on in the process. Then, just to make note of the starting point here, sample C has a much more soap content in the formulation compared to the others, and that's why you have a higher starting point. Again, of very interest is sample E, which is a blend of A and C. And I think in the very first slide, when I had the characteristics of the oil, you also saw that the pour point as well was saying the same kind of trend. Right, so just some discussion or conclusions about that. So these two sort of test methods have verified the trends. They were both giving the same results. So sample C, as we know, had more paraffins there. This showed a very poor low temperature response. Even though this oil is a group 2 and it's been through a more severe process of hydrocracking, it's still not sufficient enough to remove any of the waxes. So we have this crystallization still taking place. Whereas samples A, B, and D, they are all naphthenic oils, and even though they are refined in very different ways, but they are all based on wax-free crude, and that's why you don't see any of these any influences in the cold temperature properties. So now looking at the high temperature analysis, right. I decided to investigate the frictional behavior at high temperature being 110 degrees, because this was a lithium-based grease, so these are typical multi-purpose greases. We usually have recommendations of maximum application temperature of 110 to 120 degrees C. So a mini traction machine was used to develop Strybeck curves. And also I had some ECR results or electrical contact resistance results. I'll explain a bit further. So this is a ball on disc setup. You might not be able to see, but you generally have a ball here and the disc. And there's a picture there. That's the disc. Because of the mini traction machine, there is an issue about the grease in the test rig moving out of the contact zone, and then the results that you get are not accurate and not representative. So there is a sort of plastic piece there that was sort of attachment placed on top, and that was to ensure that the grease was staying in place, and so you could rely on the results. We used a sliding rolling ratio of 80%, and that was determined experimentally, as this is a ball on disc setup. So if the ball is supposed to be rolling, it will not roll 100%, but at some point it might slip or slide. So you try to determine the sort of optimum slide to roll ratio, and then you can set your instrument accordingly to get acceptable results. We ran 5 cars and took the average of those. For those, this is just a quick slide on Strybeck curves. It's a good way to just get a quick idea of the different lubrication regimes. So basically the curves are the friction coefficient on the one axis and viscosity, speed times load on the other. And your curve will typically, the boundary lubrication is when you have almost metal on metal contact, and the asperites are touching quite a lot, whereas with a mixed lubrication regime, you have some separation of the metal contact with the fluid film or the lubricant, and then you get a full lubrication or hydrodynamic lubrication, where the 2 pieces of metal are completely separated from each other. So it's a very useful tool model used in tribology. Okay, so these were the greases at 110 degrees. So interesting is that we have at the bottom the speed, in millimeters per second. We have very low friction coefficients to start with, and then they increase, probably a type of running in, and then they move. So they do all kind of follow a similar type of trend. But when we have a close look, we see sample A, which is dark blue here. That was one of the naphthenic oils that was the least refined oil. And that was blended, of course, with sample C, which is here. And in a way, it's showing actually the best friction coefficients, I would say, or the lowest overall. And sample E is the red one, which interestingly enough is following the trend of sample C up until that point, and then it crosses over and probably follows the trend of sample A. Because remember, A and C are pretty much blends of sample E. So again, we are still seeing some very interesting synergies between, specifically, like I said, group 2, the naphthenic oils, and then that being carried through into the performance of the greases at high temperature as such. Oops. And then just looking at some of the other oils, not performing too well. Sample D is actually a naphthenic oil that is solvent refined. So for us it's interesting to see if we take a naphthenic oil and we only use it as a solvent refining process, or if we use only a hydrogenation process. So there's different molecules in these oils, and they tend to be performing differently in these kind of situations. So that was something interesting for us to see. So it seems like the more highly refined naphthenic oils seem to have a poor performance when it came to friction. Right, so I wanted to understand, before we forgot, the ECR. So this is the electrical contact resistance. Now 100% means that the two pieces of metal are completely separated from each other, and you have a fluid, a film between, a tribofilm in place. So here we see that sample E performs quite well at certain speeds. It does probably have some boundary type of lubrication, but for the most part it's a fairly good result. Whereas sample A is there, and sample E, sorry, A, right, I wanted to show how, again, the more highly refined naphthenic oils are showing poor friction performance. Right. So I wanted to understand how the oils would behave in the same kind of test rigs, but unfortunately we had to just use what we had at our disposal at this point of the project. So we did have a rheometer, and I had a tribosol attachment to the rheometer, so I was able to run Strybeck curves on a rheometer. So the setup here is that you have a steel ball and 3 plates, and I set the same force of 20 newtons, and we use the same temperature at 110. So basically, if you can see it, these are not the right plates, but I had metal plates here, so you've got 1, 2, 3, and you've got the ball, and then you submerge the oil, and you can generate Strybeck curves from this instrument. So here we have some nice typical Strybeck curve type graphs. Again, we see these interesting trends. Firstly, that the graphs here are all completely inverted compared to the grease ones. So with the grease results that had a very good performance, the oil is showing the very worst performance. So it seems like we have quite interesting things at play. I think maybe the soap content could be influencing. We think that also, obviously, the viscosity index of the oil could have a big impact because the sample, this test is run at 110 degrees C. So here the sample A, which is a dark blue, they are showing quite a okay performance, and but sample E, which is the blend of the two oils, pretty much also follows this the trend halfway, I should say, between A and C. So this again proves synergies between naphthenics and group 2. Right, that's just some conclusions. Oops. Sample C was displaying the lower friction results. We think this is because of the thickener content and also the viscosity index of the oil. This is the group 2 paraffinic oil. Sample E, which is the blend of naphthenic and paraffinic, increasingly follows the same trend as sample C and at lower speeds, but then switches over to sample A at higher speed. So here we couldn't really conclude that the viscosity of the base oil was actually influencing the thickness of the oil film on the contact zone. So we think that there are a lot of other things at play. So just some brief conclusions. So firstly, the use of naphthenic oils in grease production can result in higher yields, meaning lower soap consumption compared to a paraffinic group 2. Interestingly enough, among naphthenic oils, those with the lower refinement degree are the ones presenting the better results. And then, of course, by blending a paraffinic oil in a group 2, a naphthenic oil and a group 2 paraffinic oil, you can have the same yields as those for pure naphthenic base oil. And then looking at the greases, you get the benefits of both the paraffinic and the naphthenic. So you get excellent low temperature behavior, and at the same time, you can get the high temperature performance of the paraffinic oil at the friction results. So really, to respond to my first slides at the beginning, how do we think the market will adjust to the ongoing changes, especially in Europe with the rationalization of Group 1? We think that for the lubricant industry, those who cannot get Group 1, they will think about converting to Group 2 or Group 3, or converting purely to naphthenics, or looking at blends of Group 2, Group 3 with naphthenic oils. And so with this in mind, we at Nynas have purchased part of the Shell refinery in Hamburg, Germany. And from the beginning of next year, we will have 330,000 tons additional capacity of our naphthenic specialty oils. So we see this as a good opportunity for naphthenic oils, and we see ourselves as positioning ourselves in the market to respond to the changes that are happening and securing a good future supply of naphthenic specialty oils. Thank you.